Stripping down science. The Naked Scientists.
Now here's a question. Why did my dishcloth detonate in my microwave? That is indeed one of the questions we will be answering for you this week, as well as finding out how wind and turbulence arise and whether mining can alter the Earth's orbit. Hello, it's Sunday the 1st of April 2012, but no fools here on The Naked Scientist because it's our science phone-in show. I'm Chris Smith, and with me this week are physics guru Dave Ansell. Hello, Dave.
Hello.
And also our naked astronomer Dominic Ford. Hi, Dominic.
Hello, yes, and also coming up, a new breed of mini rocket engines that could take probes to the Moon and Mars for a fraction of the current cost, and how pesticides are poisoning bumblebees.
And I'll be heading outside with a microwave and a dishcloth to see if I can recreate the accidental scourer-powered mini inferno reported by one of our listeners.
And he has really got a microwave on a trolley outside. I can see it through the window. If you have any questions or comments for us, here's how you can get in touch.
Write on our Facebook page, that's at facebook.com/thenakedscientists, or drop us an email. Our email address is chris@thenakedscientists.com.
The Naked Scientists podcast is powered by UK Fast, the UK's best hosting provider. On the web at ukfast.co.uk.
Now I'm going to kick off with a challenge for everybody. So, Dominic, you can help me out too. Do you know, Dominic, what the 9-dot problem is?
9-dot problem? Not sure I've heard of it, no.
OK, well, Oliver is also on the phone, and I'm going to ask him too. Hello, Oliver.
Hi, Chris.
Are you acquainted with the 9-dot problem?
No, I'm not.
OK. I'd like you both to have a go at this. OK, you don't have to solve it during the scope of Oliver's phone conversation, but we want everyone out there to have a think about this. Do 3 dots in a row. OK, space them about 1 centimetre apart.
So I've drawn 3 dots in a line.
Now go about a centimetre down and draw 3 more dots under the first set of dots.
So 3 more dots, so 6 dots now.
That's right, and then underneath those, another 3 dots about 1 centimetre down.
OK, so now I've got 3 by 3 grid of dots in front of me.
Are you with us so far, Oliver?
Yep.
OK, now what I want you to do is to, without taking the pen off the paper once you've started, draw 4 lines. They've got to be straight lines, and I want you to connect every single dot with your 4 lines, and you mustn't retrace any of the lines. Okay, so 4 straight lines, connect all of the dots, do not remove your pen from the paper, and do not retrace any of the lines. Have you got that, Oliver?
Yep.
Okay, so that's the challenge for you and everyone else who's listening to the programme to see if you can solve the 9-dot problem. Meanwhile, talking of problems, Oliver, welcome to the show. I understand you have a question for us.
My question is, why do energy-saving light bulbs take so long to get bright? And why is this brightness still dimmer than conventional light bulbs' output?
OK, this is all to do with how an energy-saving light bulb works. A conventional old-fashioned light bulb basically works by putting a lot of electricity through a very thin wire, and it gets very, very hot. And when something's hot, it glows. And at about 2,000 degrees centigrade, which is the temperature of the filament in a normal light bulb, it glows pretty white, so you get slightly yellowish white. And the problem is, though, that about 90% of the light it's giving out at that temperature is actually in the infrared. So it's a hideously inefficient way to make light.
It's just giving you heat, which you can't see.
Yeah, you can't see it. It's entirely wasted. So what you do in an energy-saving light bulb is you create light in a very different way. You give energy to a mercury gas. You basically pass a spark through a mercury gas. That then gives the atoms extra energy. They then release that in the form of ultraviolet light and very, very little infrared. The ultraviolet light then gets converted into visible light by some phosphors on the inside of the tube. These are the sort of things which your clothes are normally full of to make them glow brighter in the sunshine, and the reason why your clothes glow if you go into a nightclub or something like that. The problem is, though, when it's very cold, mercury is normally a liquid at room temperature, so the mercury isn't much of a gas. So it's the lights have got to warm up a bit until there's enough gas in there to produce the full brightness. Why aren't they quite as bright as they should be compared to a normal light bulb? That's probably mostly to do with the manufacturers being slightly optimistic on the how bright they actually are.
So if you put more of the ingredients in and a bit more energy in, you should be able to get the same amount of light out. They're just being a bit overambitious.
Yeah, I think they used to quote it as being 7 times more efficient than a conventional light bulb. These days they're supposed to use 5, and I think with 5 then they should be equivalently bright.
Oliver, does that sate your curiosity?
Yes, thank you.
Brilliant. Well, it's been good to have you on the show. Thanks for calling in.
Bye.
Take care now. Hello, Paul.
Hello.
What can we do for yourself?
Something that's always intrigued me on sunny days like this, when I'm inside the house, I'm fine, I go outside and I start sneezing. Now, I don't know anybody else that this happens to, so do you have an explanation, please?
I think you've got what's called the photic sneeze reflex.
Okay.
Photic as in light, sneeze as in, well, sneeze. This is apparently genetic. It seems to run in families. Do you have any family members who do the same thing?
I don't actually, no. I've got family members, but I'm the only one that does it.
OK, it affects about 1 person in 5, and what scientists think is going on is that there's a little bit of miswiring in the brainstem, which is the thing that connects the spinal cord to the main part of the brain, which is where all of the circuitry is to control the size of your pupils and blinking and that kind of thing. Right. So when a bright light shines into your eye, the same circuits that get activated to cause a blink and your pupil to shrink, pupilloconstriction, some of the nerve activity also spills over into the parts of the nervous system that detect irritation in your nose, and they trigger a sneeze. People used to think it was because sunlight made your eyes water and that the tears running down into your nose tickled your nose a little bit, and that triggered the sneeze. But when they did careful studies, and in fact the military have been doing this, because what you don't want is someone who's flying a supersonic jet to suddenly develop the photic sneeze response when they're flying into the sun and then have a fit of sneezing at the flight controls doing 1,000 miles an hour. So they were looking into this, and they ruled out the tears tickling the nose, and they think it's actually this miswiring. It does appear to be, as I say, familial. So you get some people who have it sporadically and some who say, yep, lots of people in my family have this. So you have the photic sneeze reflex. It happens to me when I get up in the morning in the winter time and I go into my shower where the lights are very bright, and you turn the bright lights on all of a sudden and you go from dark to very bright, and I have this sneezing fit.
That's really interesting. Thank you. I never thought it was anything like that.
Pleasure. Great to have you on the programme, Paul. Thanks for calling in.
Thank you. Bye-bye.
Quick one for you, Dominic. Alan Alderson asks an intriguing question, actually. He says, how does the universe come by its angular momentum? The universe is full of angular momentum. Planets rotate around, and stars revolve, and galaxies themselves are turning. But if there was a Big Bang which pushed everything outwards from one point source, where did things start spinning from in the first place?
Well, that's a good question, but you don't actually have to have any overall rotation in the whole universe for objects within the universe to be rotating in various different directions. Now, imagine that you've got a large cloud of gas that has no rotation to begin with, but that you split it up into lots of little pieces, which go on to form into lots of different galaxies. Now, each piece, by random chance, will have some particles which are swirling around in some particular direction, more than it's got parts which are swirling around in other directions. So it will have some very tiny rotation in some particular direction. Now, as that cloud collapses down to form a star or a galaxy, there's an effect called the conservation of angular momentum, which means that spin is accelerated as the object gets smaller. And that's similar to the effect that if a figure skater is skating on ice and they start off spinning quite slowly and they pull their arms in, you'll see they start spinning incredibly quickly. So that means that an object, even if it's only got a tiny rotation to begin with, can actually end up rotating quite appreciably, as we see planets and stars in the universe doing. And certainly if you look at the rotations of different stars, you will see that smaller stars tend to rotate much more quickly than bigger stars, and that is because they're being spun up as they've contracted down.
Super. Dominic, thank you very much. We do a similar sort of thing with our kitchen science experiment with the flame tornado, don't we, Dave, when you have air coming in from the side through a rotating grill, moving towards a rising column of hot air caused by a flame, and that causes the air to spin up in the same way Dominic's outlining. Now, talking of experiments, just remind people what you have got set up in the car park to tantalise us with later.
Well, we were asked by someone who was obviously doing something odd. They had put a dishcloth in their microwave. We'll be talking to him later. And he discovered it caught fire. And he was a bit confused by this, so he's rung in. So I'm going to be recreating the experiment and trying to work out what it is about the dishcloth which causes it to catch fire.
Brilliant. Dominic, Benjamin Lunsky says, "Hi, Dr. Chris, enjoying your radio show. What causes elliptical planetary orbits?" This is a good question because, of course, the gravity is pulling the planet towards the thing it's orbiting, like the star in the middle, for example, but it's pulling it the same in all directions. So why should the planets go round in an ellipse, a sort of squashed egg shape, rather than in a perfect circle?
That's right. So the simplest kind of orbit is a circle, where the planet is trying to travel in a straight line, which is carrying it further away from the star it's orbiting around. But the gravitational pull of the star in a particular direction is pulling it back, so it's staying at a constant distance from the star as it goes all the way around that central star. Now, if you imagine that the planet had slightly less speed, then it wouldn't have enough speed to keep at the same distance from the star, so it would begin to fall in towards the star. And as it begins to fall in, it will start to move much more quickly because the star is pulling it in and it's gaining kinetic energy, but it's then moving too fast to be in a stable circular orbit that much closer to the star. So it then has enough energy to move back out again. So it's, if you like, wobbling in its distance from the central star.
Thank you very much, Dominic. Peter's on the line. Hello, Peter.
Good evening. I just have two questions, if I may. One is, the aircraft flies into an area of air turbulence. Is this turbulence caused by a varying wind speeds or crosswinds or a change in air density?
Interesting question, Peter. I've also got a question from Kai in Essex, who says, when there's a 3 or 4 minute gap between each plane and the planes are taking off, is that due to turbulence? Maybe you could tackle both of those, Dave.
The general air turbulence you're getting in an aircraft, you're flying through the air at about 500 miles an hour. If you're flying through beautifully smooth air where it's either all moving, is not moving at all, or it's all moving at the same speed, you'll have a nice smooth journey. But if you're in complicated, messy air, so if there's wind blowing off a rough surface, or if there's areas where the air is moving upwards and areas where it's moving downwards, somewhere it's going sideways. As the plane flies through these, it will suddenly be flying too fast and have too much lift, so it will go upwards. Then it will suddenly be flying too slowly, it will go downwards, it will fly into upwards moving air, moving downwards moving air, sideways moving air. So it sort of gets shaken around because it's going through these little pockets of moving air very quickly, and you feel it is kind of being shaken around all over the place. The thing with aircraft not being able to fly very close to each other is related. It's because when a plane flies through the air, it's pushing lots of air downwards, and this creates, over its wings, the air at the side isn't getting pushed downwards, so it kind of gets lifted upwards, and you get these two kind of swirls, these two vortices, one at the end of each tail. And from a small plane, those aren't very dangerous, but from something like a 747 or an A380, those are incredibly powerful. There's a huge amount of energy in these things. And if a small aircraft gets caught in one of those behind a large aircraft, it can get flipped upside down and can crash really viciously.
So you don't want them too close for that reason, which is also why mid-air collisions or near misses are so important as well, I suppose.
Yes, if you had a near miss flying into these vortices, wake vortices from another aircraft, you could cause problems, but it's not as bad as near the ground, because if you're up high, you've got more time to deal with the fact you're now upside down. If you're at 100 feet, you don't have any time at all, and it's very messy.
Now, Peter, what's this? You're talking about ties as well. You've made an observation.
I've noticed that a lot of the men's neckties are striped neckties. The stripe starts on the top left and go down to the bottom right. I mean, you have a few exceptions to the rule, but so the question is it just a most effective fashion statement, or is there some sort of obscure psychological reason for this phenomena?
Peter, thank you for the observation. We'll ask the audience, can you help Peter and explain why gentlemen's neckties seem to go from top left down to bottom right? Is there a psychological fashion statement reason or some other? Dominic, you have a theory.
Yeah, well, I was thinking about this yesterday, and I was wondering whether it was to do with people reading from left to right and top to bottom. But I'm told that in America, ties slant the other way.
Really?
So that suggests it's a fashion statement. I'm not sure. Perhaps if some Americans could tell us.
Yes, so if you're listening and you own a necktie that bucks Peter's trend or Dominic's trend, then do tell us, chris@thenakedscientist.com. Dominic, you have been looking at what went on around, I suppose, our sun 4.5 billion years ago when the solar system was forming.
That's right. This is uncovering some new clues about the formation of complex carbon-based molecules that make up all of the living things on the Earth. Now, you need two conditions to form large molecules. You need ultraviolet light, which has enough energy to break apart simple molecules into highly reactive components. And then you need some kind of heat source, which can jiggle those components around and rearrange them into different configurations. One environment which has up until now been ruled out as a possibility are protoplanetary disks. So these are the systems out of which new solar systems are forming. And the reason why those have been thought unable to form large carbon-based molecules is that only the very central part of those disks is exposed to the star's ultraviolet radiation, because they're so thick and dense with material that the ultraviolet light is absorbed in the very most central region. Now, what Fred Chesler and Scott Sanford have argued in Science this week is that based on computational simulations, the material is not continually orbiting around at a constant distance from the star, it's all mixing around. And even if it's only for a very short period, any given piece of material in that disk will from time to time pop out the top and bottom of the disk, and for a period of perhaps 1,000 years, it will have quite a clear line of sight to a central star.
So it will see some ionising radiation, which could help to rearrange the molecules.
That's exactly it. Even if it's only for a window of 1,000 years and a lifetime of 1,000,000 years for this disk, in that 1,000 years you can get a lot of chemistry done to start forming large molecules. And that suggests that you can potentially form quite large quantities of hydrocarbons and alcohols and so forth in the early lives of solar systems like our own.
But those are pretty simple molecules, aren't they? So are you arguing then that those are the building blocks to then build up and make them into more complicated things like proteins or sugars or bigger molecules that we find on early Earth type environments?
That's right. These are called prebiotic molecules. You need them to start the process towards forming proteins, but we don't yet really understand where or when these simple building blocks were assembled into more complicated molecules in life.
Dominic, thank you. Frank in Ipswich got in touch and says, with reference to striped ties, this may have its origin in heraldry, with the left-handed being sinister versus the right-handed being dextra. But why should that explain why we go left top down to right bottom? And is this true in America? Meanwhile, if you have a question for us here at The Naked Scientist, you can email chris@thenakedscientist.com. It's been the National Astronomy meeting this week, and our own Ben Valsler has been along to take a look at what's going on. Ben, first of all, what is NAM?
Well, NAM is the annual meeting of the Royal Astronomical Society, although this year was a little bit special because it was in partnership with the German Astronomical Society, the Astronomische Gesellschaft. It's sponsored by the STFC and the University of Manchester in this case, and it was held in Manchester University. There were nearly 1,000 delegates, hundreds and hundreds of presentations, exciting public events, plenaries, and some fun social stuff as well.
Now, of course, you make Naked Astronomy,
Yes.
which is our podcast that Dominic also appears on, so I presume this is going to turn into an episode of Naked Astronomy. But without giving the game away too much, what were the top stories that you saw this week?
The one that seems to have really gathered the most coverage is an image that's been called the Billion Stars photograph, even though there's actually far more than 1 billion stars in it. It's a photograph of the Milky Way put together by people at the University of Edinburgh from images taken by 2 different infrared telescopes. There's the UK Infrared Telescope in Hawaii and Vista, which is in Chile. All in all, it comes to 150 gigapixels. Now, if you think that your digital camera might be 10 megapixel, that's 1,500 photos tiled next to each other. They worked out that if you were to print it out, it would be about 200 metres wide. So it's a huge image, and it's an image of our Milky Way.
Nice, but why is it important?
Well, it's very useful for testing algorithms that are designed for spotting interesting or unusual objects. And it's part of something called the Vista Data Flow System. And the idea is that we use this to calibrate new telescopes and essentially to archive astronomical data, so people can easily use that image to give us an idea of what is actually there at a given time in the Milky Way.
Meteors?
Yes, well, it's also been found that Jupiter and the resonant orbits between Jupiter and Halley's Comet are responsible for when we get spectacular meteor showers, which are known as meteor outbursts. Now, there was one of these back in 1993, another one in 2006, and now researchers at Amman Observatory in Northern Ireland think that this is because of the gravitational impact of Jupiter, which sort of slightly restricts the orbit, so you get a bunching up of the stuff that falls out of Halley's Comet. When we then go through that bit of the tail in Earth's orbit, we get this spectacular meteor shower, and they think.
But we've got to live another, 60 years to see it, haven't we now?
Well, the next one is going to be in 2070, yes, but they do argue that there's still an awful lot of good science that we can do between now and then.
Terrific. And finish us up by telling us about the dark energy material they presented.
Well, this is based on the Sloan Digital Sky Survey 3, and using an instrument on there, or a survey called BOSS, that's the Baryon Oscillation Spectroscopic Survey. What they've done is looked at over 250,000 galaxies and essentially done a statistical analysis where you can see how they clump together. And the clumping together can give you some idea of the waves that formed in the very, very early universe before atoms even formed out of the incredibly hot plasma. These waves sort of got fixed in place, so if we look at these waves at different times, we can look at the expansion of the universe by looking at the size of those wavelengths. And they have worked out that dark energy, this incredible force that is driving the expansion of the universe to get faster and faster, seems to have taken over somewhere between 5.5 and 6.5 billion years ago. So before that, the dominant force in the universe was gravity holding everything together. And after that, it's been dark energy that's been causing the universe to expand. Now, that won a Nobel Award when it was first discovered. So now, working out what it is that's doing it is a big question in astronomy.
It certainly is. Ben Valsler, thank you very much for coming and telling us about that. You can find out more about those exciting stories, I'm sure, when they're published in our Naked Astronomy podcast later this week. Ben, thank you. Now, what was the atmosphere like on the Earth nearly 3 billion years ago? Well, that's a pretty tough question to answer. But, incredibly, some fossilised raindrops, or rather the patterns that they left behind when they fell 2.7 billion years ago, have enabled scientists to reconstruct some aspects of what the air that rain fell through would have been like. And with us to explain how, from the University of Washington in Seattle, is Roger Buick, who's one of the authors on this study. Hello, Roger.
Good day.
So what are you actually trying to understand about the early atmosphere?
Well, what we really want to know is why the Earth wasn't an ice ball 3 billion years ago. The sun was only 80% as bright then as it is now. And if the atmosphere was the same as it is now on the Earth, the planet should have been completely frozen over.
Yet we've got geological evidence of there having been running water in quite a balmy climate.
There's abundant geological evidence for liquid water, oceans, rivers, lakes, and now rain as well. Either we had to have a much denser atmosphere, or else we had to have a whole lot more greenhouse gases in the atmosphere to keep us warm. And there's been a debate going on for 20-odd years as to what sort of atmospheric warming mechanism was active on the early Earth.
And obviously without the capacity to go back 3 billion years or so and take a snapshot of that atmosphere, we're forced to rely on sort of indirect measures, which I guess is what you've done in this paper in Nature this week. You've used an indirect measure to work out what the atmosphere must have characteristically been like.
Yeah, well, until Torricelli invented the barometer, we've really got no real readings of what atmospheric pressure was like early in Earth history. The atmosphere has a very, very indirect and faint impact on rocks that can get preserved from early in Earth history. So to be able to register anything about the atmosphere from early in Earth's times is really quite remarkable.
So how did you actually do this?
Well, we found some literature records of raindrop imprints in rocks almost 3 billion years old. There's a number of places in the world where there are these ancient raindrop craters, and the best ones that we were able to come across were in South Africa, out in the Karoo Veld. And so we went there and took samples of them and made latex peels of them and measured them. Now, there's a relationship between the size of raindrop imprints and the speed at which the rain fell. And the speed at which the rain fell is influenced by the atmospheric density. The denser the atmosphere, the slower the raindrops fall, So the smaller the little craters that they leave.
So how do you work out, based on the rock samples you've got from 3 billion years ago, how big the craters should be in proportion to the speed of the raindrops? How did you close that gap in our knowledge?
The big variable is the nature of the material being impacted. The South African raindrop imprints were in volcanic ash. So what we did was get some equivalent modern volcanic ash from the Icelandic eruption a couple of years ago and did experiments by dropping artificial raindrops down a 7-floor stairwell onto a pie plate full of
this high-tech stuff, this. And so that was your sort of proxy measure. You could see, based on how fast, or therefore how much energy, how much momentum the raindrops had, how big a splatter imprint they make. And this means you can extrapolate from the latex peels from the South African rocks how fast the raindrops must have been going 2.7 billion years ago.
Exactly. The other variable, of course, is the size of the raindrop. As anybody British will know, raindrops vary greatly in size depending on the intensity of the rainfall.
Well, at the moment we're in drought in the southeast, so we won't any rain at all. So zero is the size.
Then.
But so what did you do to constrain that?
We do know that there is an absolute maximum size to which raindrops can get. It's a proportion of the interplay between the surface tension of the water and the force of gravity trying to pull it to bits. And so the largest that's ever been recorded on the Earth and the theoretical maximum size from physics is 6.8 millimetres. So that sets a maximum bound on what atmospheric pressure could have been. But it's unlikely that the absolute maximum raindrop size was achieved. Probably more like 5 millimetres was the realistic maximum raindrop size.
Putting all that together, what does this tell us about the atmosphere 2.7 billion years ago when these, what are now rocks, were just volcanic ash and this moderate shower was falling on them?
Well, it tells us that the maximum possible atmospheric pressure was about 1.6 bars, so 1.5 times what it is now. But more likely, it was 1.1 bar, 1.1 atmospheres, or maybe even as low as 0.6 of a bar. So only 6/10 of our current atmospheric pressure.
So very, very similar to what we have today, which argues that we couldn't have had this blanketing smog of CO2 giving us an artificial greenhouse effect to keep the Earth warm then.
That's right. Most likely we had to have some other sort of greenhouse gas other than just carbon dioxide in the atmosphere to warm the Earth. Maybe something like methane. Though that's problematic. If you have high levels of methane in the atmosphere, you produce a haze of organic particles formed by ultraviolet light, and that reflects sunlight and has an anti-greenhouse effect. Other possible greenhouse gases would be, my favourite is laughing gas, nitrous oxide. There's some evidence that there was a biological nitrogen cycle producing laughing gas back as far as about 2.7 billion years ago. So laughing gas is something like 100 times more effective as a greenhouse gas than carbon dioxide. So we might have had some methane and some laughing gas in the atmosphere as well.
Imagine existing in that climate. Roger, thank you ever so much. That's Roger Buick. He is from the University of Washington in Seattle, and you can read the work he published and was just talking about in the journal Nature this week if you want to follow it up.
Distilling the best science. The Naked Scientists.
You're listening to The Naked Scientists with me, Chris Smith, and with Dave Ansell and with Dominic Ford. Dave, we've got this question, which you can probably answer very well, from Andy Fletcher, who says, can mining alter the Earth's orbit?
In order to change the Earth's orbit, you've got to somehow apply a force to the Earth. Now, mining is just moving material around on the Earth. So we might dig stuff out of the ground, move it to the top of a skyscraper, or even burn it and move it into the atmosphere. Now, this could conceivably have a very, very tiny effect on how the Earth is rotating, because if you change the shape of the object, it will change how it rotates. But you're not applying any forces to anything else in the universe, so you can't affect how the Earth is moving. The only conceivable way it might slightly affect things is you might get very, very, very minute effects whereby a slightly different shaped Earth might feel sort of tides from from the Moon and other planets microscopically differently, which could slightly change the Earth's orbit. But the effects are going to be kind of tiny effects on tiny effects on tiny effects, so far, far, far too tiny to be measurable.
And now just time for this illuminating question.
Hi, naked scientists. I would like to know why most street lamps are orange and not nice bright white, please. Thank you, from Karina, age 7, from Bishop Stortford.
Well, Karina, the reason that most streetlights are orange is because they contain the chemical sodium. And the way the light works is that some electricity is passed into the light bulb, and this gives energy to the sodium, and the sodium, when it gets excited by the energy, gives out a lot of orange light, making it a very cheap and a very efficient way to illuminate a very large area. But to produce white light is much more complicated, because to make white light you have to mix lots of different colours of light together, and it's the mixture that looks white. And the way in which the lamp designers make this happen is that they use different chemicals in the light, and each of those chemicals get excited, and they then produce different colours of light, which you then see mixed together, and it looks white. And because it's more complicated and involves more chemicals, it's more difficult to do and it's more expensive. And since orange light does a good job, most of the time we use orange sodium lights rather than using white ones. Jeff in Great Massingham, Dominic, says, with the recent solar activity that's been pummelling the Earth's atmosphere, will this eventually dissipate our atmosphere? But we are talking millions of years, he emphasises.
Eventually, yes, it will, in about a billion or a couple of billion years' time. The sun is very slowly warming up and expanding. It's mostly in a steady state between pressure pushing the sun outwards and gravity pulling the sun inwards. But over time, the pressure is winning ever so slightly and causing the sun to expand and get brighter. But in terms of the oceans boiling, that's about a billion years away. In terms of the Earth losing its atmosphere, that's a couple of billion years away. I mean, it's 5 billion years until the Earth would actually fall into the sun and we would be burnt to a cinder.
Oh, that's a comforting thought. Thanks for that, Dominic. Dave, tell us about this amazing engine, this little engine, a propulsion for spacecraft.
That's right. A rocket has been developed that could get a space probe from low Earth orbit all the way to the moon with using just 100 grams of fuel. Now, we're not talking Apollo missions here, we're talking nanosatellites, very small satellites, maybe only a kilogram in weight.
But with modern day electronics, I mean, you can pack a lot of science or a lot of technology into just a kilo, can't you?
Yeah, they're getting very fashionable at the moment. They're not good for things like telescopes where you need something very, very large, or a communication satellite where you need a lot of power. But there are many questions which are very much better answered by lots of small satellites, or just much cheaper with small satellites.
Things like gravity fields or magnetic fields and things like that, for example.
Yeah, that's right. Or even exploring a planet. You might not be able to do the in-depth detail, but if you want to look over a large area, it's a lot better to use small probes rather than one big one.
And how much does a big one cost?
Well, the big ones, you're talking a couple of $100 million, whereas these small ones, maybe even only $500,000. So much, much cheaper, and they can piggyback on the ride with another satellite going up there. So the launch costs are a tiny fraction of a major satellite.
So what's holding back the field at the moment? Why aren't we seeing droves of these nanosatellites out there swarming through space and doing these sorts of studies at the moment?
Well, at the moment, there isn't really a practical rocket for them. Chemical rockets are very, very heavy and involve gases and big valves and things like that. There are rockets called ion rockets, which essentially throw the stuff out the back 10 times faster than a chemical rocket, which means you get 10 times as much thrust for every kilogram of fuel, and because you don't have to carry so much fuel, you don't need as much fuel, and it all gets much better. But those tend to use xenon gas, and containing that, you need big, heavy containment systems, and also you need valves, and it's quite difficult to shrink.
These are these ion drive engines, aren't they? That I think Smart 1 was one of the first examples, and that went to the moon. It crash-landed into the moon eventually when it ran out of fuel fairly recently. But that idea is, as you say, you take xenon gas and you ionise the gas so it has a positive charge. and you accelerate it, using electricity to then give the particles some momentum so they're then thrown out of the back of the craft.
Yeah, you're essentially using energy from the solar cells, so you're not having to take the energy with you, which makes it much lighter, and then you throw these ions out the back incredibly fast, so you get a lot of push for every gram of fuel.
Well, that sounds good, but like you say, heavy gas cylinders, lots of valves and things. What's the alternative, though?
Well, a Dutch company called EFPL has managed to build an ion thruster which is only 200 grams. They've done it by not using the xenon gas. They've been using something called an ionic liquid. This is essentially a liquid made up of positive charges and negative charges. If you melt salt up to sort of 600-700 degrees centigrade, that's an ionic liquid, but there are other ones which will stay liquid down to the minus 100 degrees centigrade, the cold in space. And also they just don't evaporate because of this very strong attraction between the positive and negative charges. So even in a vacuum, you can just have it sitting there in a bottle and it's very, very easy to deal with.
So it's basically the same thing as the ion drive engines we've had before, except instead of using a gas like xenon gas, you use one of these ionic liquids and you throw the liquid out of the back, having accelerated it, and that pushes your craft along.
There's a couple of other neat things which they've got. One is they don't need any pumps to move it around because they're just using capillary action. So a bit like if you put a cloth into water, the way the water pulls up, they're just using those forces. They're also making their rockets absolutely tiny using the similar technology used for make a computer chip. And instead of just throwing out the positive ions, they're going positive, then negative, then positive, then negative. And the thrust is very, very small, only equivalent of about a square centimetre of paper on Earth, but it can keep on firing for years. So one of these, on 100 grams of fuel, could get a kilogram probe to the moon. You could send them further out to Mars, and it would be very fascinating to see what science could come from these kind of probes in the future.
What an ingenious idea. There's an awful lot that scientists can learn from the past about fossils. But one particular extinct species is proving a very tough nut to crack. Dwarf elephants last roamed the Earth more than 10,000 years ago. About a metre tall, fully grown, they're even considered by some to be responsible for the legend of the one-eyed Cyclops. But although they've been studied for 150 years, fundamental information about dwarf elephants is still missing, and no one's exactly sure how the different species evolved. Paleontologist Victoria Herridge from London's Natural History Museum is part of an international project trying to solve the mystery. Victoria studies dwarf elephant fossils found on a number of Mediterranean islands, and Sue Nelson went to meet her in one of the museum's basement stores.
In here we have a whole drawer full of dwarf elephant teeth from Cyprus, and they're all different sizes, but most of them are smaller than the size of my hand, which sounds quite big for a tooth, but for an elephant tooth, that's absolutely tiny. They have 6 teeth through their life, and as the elephant grows bigger, the teeth grow bigger. So the smaller teeth are actually the teeth of younger elephants. It seems that on islands, when big animals become isolated there, they tend to evolve to become smaller, and conversely, the small animals, like mice and rats, tend to evolve to become larger, which is an interesting phenomenon we call the island rule.
As this project wants to look at the different environmental changes and the effect that had on the species, I assume then that means that you suspect that the change in climate had something to do with their evolution, why they became the size they did, perhaps why they became extinct as well.
Yes, certainly a possibility. If you look at modern-day islands, we know that the number of species that live on an island is related to how big the island is and also how difficult it is to get to that island from the mainland. So because there's this relationship, it seems sensible to assume that islands in particular and the animals that live on them might be affected by sea level change. So if the sea level was to rise, as we fear it might do in the next few years, you would effectively see a greater impact of that on islands. So using that as a starting point, we then thought, well, the period that we're interested in, which is called the Quaternary, so the last 2.5-3 million years, a lot of that was characterised by these shifts between ice ages and warm stages, and that will then be followed by a rise in sea level. So we think, for instance, at the peak of the last ice age, the sea level was 120 metres or so lower than it is now.
Wow.
Yeah, so quite an extreme difference. But because it's happened several times, so about every 100,000 years, what you've got there is a repeated example of this situation changing. So we aren't looking at the effects of the climate per se, it's more the associated impact of that climate change, i.e. sea level change, that may affect the environment in which animals find themselves. Now, Sicily is very, very close to mainland Italy. But the sea that separates the two is about 100 metres or so deep. And so 120 metres of sea level drop would join Sicily to the mainland. It would also, interestingly, join Malta to Sicily. And so at low sea level, what you might get is, if you like, the mainland kind of reaching out and encompassing Sicily and Malta, and that would become part of the mainland. Now, when the climate shifted again, and you got a change from, say, an ice age back to a warm stage, then, of course, sea level would rise, and you'd find yourself with two islands, Sicily and Malta, and the animals that were there, that had effectively been mainland animals until that sea level change, now become isolated on these islands. And it's following that isolation that the evolution towards becoming smaller, we think, happened. So we're wondering whether or not you can effectively associate some of these species with some of those climatic-driven sea level changes of the past. If I just lift up this very heavy tooth here.
Yeah, you need two hands.
Yeah, two hands. This is not going to fit in one hand. This is, you can hear how heavy it is from the clunk there. But this is a straight-tusk elephant tooth from Clacton-on-Sea in Essex. So we had straight-tusk elephants in the UK, but that species actually stretched all the way across Europe down to the far south, so into Greece, into Italy, which makes sense because we think that was probably the ancestral species of these dwarf elephants that somehow reached these islands, perhaps at low sea level, and then became isolated on those islands when the sea level rose again. And when it was isolated there, it evolved from being very, very large, so a straight-tusked elephant would have been about 4 metres tall, much taller than the African elephant, which comes in about just over 3 metres, would have weighed about 10 tonnes. Contrast that again with the African elephant, the largest living land mammal, was about 7 tonnes. And that it would have evolved on those islands to something as tiny as this 1 metre tall species. And that's a very extreme example of evolutionary change. And it's a wonderful example because it obviously happened again and again on different islands. And because it happened so many times, it starts to give us, if you like, a natural experiment. These islands are kind of like a natural laboratory for evolution in real space and time. And it's a really neat potential way of getting a handle on how quickly evolution happens and potentially how and why it happens. And that's why studying these elephant species potentially will give us greater insight into much broader evolutionary and biological trends.
You can hear that report from Sue Nelson with more news from the natural world in the Planet Earth podcast. Find that at thenakedscientist.com/Planet Earth. Now, I've been tantalising people all evening with this, and we've had quite a few calls about it. Dominic, you've had a go. Have you finished? Have you got it?
No, I'm afraid my attempt was 5 lines. I thought Dave had it earlier. He was looking quite smug, but now he's looking as confused as the rest of us.
OK, so what I told you to do was to draw 3 dots in a line on a piece of paper, then underneath that draw another 3 dots, and underneath that draw another 3 dots, so you have a sort of grid of 9 dots. I said take 4 straight lines, connect all of the dots without leaving the paper with the pen or retracing any of your lines. Now, the solution, and you're going to kick yourself for this, I didn't tell you had to stay inside that square. If you put your pen on the top left dot and you draw a diagonal straight line to the bottom right dot, you then draw a line which goes along the bottom 3 dots and then goes 1 dot equivalent distance further out to the left. Now you draw a straight line up to the top right, taking in the upper 2 dots that you'd missed before, and you finish the equivalent of 1 dot further outside the box at the top right. Then you come vertically down through the final 2 dots and you've done it.
So this is quite literally a thinking outside the box problem.
You hit the nail on the head. And this is the interesting thing here, because what Alan Schneider and Richard Cheed do in their paper is that they actually take 22 volunteers, they rig them up for what's called transcranial direct current stimulation. This is where they put a small current, 2 milliamps, across the brains of these volunteers. And what they do is to apply right-sided positive current and negative to the left. So what this does is it stimulates the right side of the brain and it inhibits the left side of the brain. When they took their volunteers, none of them could do the problem. They subjected them to 10 minutes of this stimulation and immediately the success rate went to 40%, just like that. And what they speculate is that the left side of the brain, which is your dominant hemisphere, it drives the way that you perceive the world using past experience. So when you see this array of 9 dots, which looks like a square pattern, your brain perceives it as a square with, as they call it, rigid boundaries, which mean that the solution your brain searches for is automatically within those rigid boundaries, and you don't think outside the box. No one told you couldn't draw lines outside the box, but it was only if you inhibit the part of the brain that confines your thinking in that way that then you're able to think outside the box and come up with that novel solution.
It's really interesting because I was showing off slightly. I did actually get this when Chris showed it to me earlier in the week. But in order to do it, I had to make a really, really conscious effort to kind of ignore this kind of constraint and actually draw outside the box, because I'd worked out that it was impossible to do it inside the box. And it was a really bizarre kind of effort it took to do that.
I'm intrigued because I think, what else could you achieve with this kind of stimulation if you can unlock your creative side in this way? And the other amazing thing that they write about in the paper, there was one volunteer who they rejected from the study because he disclosed to them that he'd had a head injury. But when he, out of curiosity, tried the test, he solved it straight away. And they were so intrigued, they asked him, well, where was your head injury? And he said, well, when I was little, I injured the bones on the left side of my head, and the fracture to my temporal bone damaged my left temporal lobe. And so his perception of the world is much more piecemeal. He doesn't see things constrained by the collection of everything. He tends to look at things in isolation. And this problem, he found no problem solving it. The answer just leapt straight out at him. Isn't that incredible? You can read it up. It's in the Journal of Neuroscience this week. We'll now have a look at what else is making scientific headlines, including bad news for bees and a tornado that's been spotted on the surface of the sun. Here is Mirasenthilingam with our Naked Scientist Newsflash.
Direct evidence that pesticides are reducing bumblebee populations has been revealed this week in the journal Science. By exposing colonies of bumblebees to the commonly used pesticide imidacloprid, Dave Goulson from the University of Stirling found that bee colonies grew more slowly and saw an 85% reduction in the production of new queens, who are crucial for producing future bee generations. The consequences could be significant to both the environment and the economy.
If we're accidentally poisoning our bumblebees and driving down their populations, there'll be less pollination for wildflowers and therefore all the things that those plants support, all the butterflies and birds and everything else. But there's also a really direct economic importance of bees. Bumblebees are the main pollinators of some of the very nicest things that we like to eat, so blueberries, raspberries, strawberries, lots of garden vegetables like beans and tomatoes. So if we lose our bumblebees, then our diets are going to be much the poorer for it.
Bacteria that have become resistant to antibiotics could be made susceptible to the drugs by the addition of certain compounds. Presenting at the Society for General Microbiology annual meeting in Dublin this week, Marta Martins from University College Dublin combined one of 5 known pharmaceutical compounds with the widely prescribed antibiotic ciprofloxacin. When used on samples of bacteria showing resistance, this combined treatment was 6 times more effective at killing the bacteria than samples lacking these added compounds, giving a new lease of life to the drug.
We think this is a better solution instead of developing new antibiotics. With these compounds that are non-antibiotics, they are synthetic compounds, we could avoid that problem of the bug adapting to them. It will not just help to treat these multi-drug resistant infections, but also help to decrease the numbers that we will see in the hospital and subsequently in the community.
Scientists have spotted a tornado on the Sun, large enough to accommodate several hundred Earth-sized planets. Using the orbiting Solar Dynamic Observatory, University of Aberystwyth physicist Hugh Morgan and his colleagues spotted the 120,000-kilometre-high plasma tornado travelling across the Sun's surface at speeds of 300,000 kilometres per hour, driven by the solar magnetic field. The discovery was announced this week at the National Astronomy Meeting in Manchester.
It's a huge structure and it lasts for 4 or 5 hours, and it's very exciting because it's a testbed for various theories on solar magnetic field and plasma movements in that field.
And finally, a robot less than 1 centimetre in size, with the ability to respond and move like a living organism, is being developed by scientists at the University of Newcastle. Modelled on an ancient fish, the robot, named Cyberplasm, will combine cells engineered to sense light and chemical cues that feed into a central processor that in turn controls a series of artificial muscles, resulting in movement. Daniel Frankel is leading the project.
The idea is really to harness the power and control of the biological system, for example, muscle contraction and sensitivity of cells, and interface them and incorporate them into a machine. The ideal uses would be swimming into waters which may be polluted or having toxins and detecting toxins, and then, in addition, medical applications for example, reconnaissance in the body, so to speak, swimming through the arteries and veins and trying to detect and maybe even treat various diseases.
The Naked Scientist News Flash with Meera Senthilingam. And if you'd like to follow up on those or any of the other news stories you've been listening to us talking about this week, the references and transcripts of the stories are available on our website, nakedscientist.com/news. And this is The Naked Scientists, Chris Smith, Dave Ansell and Dominic Ford. The guy who stimulated our experiment this week by doing his own experiment in the kitchen, although unintentionally, I think, was Andy, who's in Canada. Hello, Andy.
Hi there.
So just very briefly, tell us what you did and what you found.
Okay, so I put a wet dishcloth in the microwave oven. It was supposed to kill some of the odor and kill some of the bacteria. And then after a few minutes, the cloth started to smolder, and the cloth had dried out. And after a while, it actually had some big singeing scorch marks. And I sent you guys a picture so you could see just how bad it got.
Yeah, it looks pretty severe.
So I need. Oh, sorry?
Yes, indeed, it looks pretty severe. So this was sort of the microwave equivalent of boiling up the dishcloth in the detergent on the hob top. You thought you'd cut corners and do it on the quick in your microwave.
Yeah, I heard of some people trying it, and I actually heard there was a scientific study where they did this and killed some bacteria. And I figured I'd try this myself, which I found out was not very wise.
Well, Dave and I were intrigued, and we were having a conversation this week about why this might happen, and we decided the best way to get to the bottom of this, as with any situation like this, is to do the experiment. So, owing to the fire risk, Hannah and Dave have left the building. Hannah Critchlow is outside with Dave now. They have a microwave on a trolley. I can see them through the glass, and they're going to attempt to do the experiment. Hannah.
Hello, Chris. Hi, Andy. And thank you very much for getting in touch, Andy, with your question that's dragged us outside to the car park with our microwave on a trolley. Dave, can you explain exactly what we have in front of us here?
Well, I have my stunt microwave, which is essentially very, very cheap, which should indicate that you really don't want to be doing this at home. And I've got 3 cloths. I wasn't quite sure what Andy had been doing to his cloth before I put it in the microwave. So I thought I would try 3 different things. One of them is very, very clean, so I've just got it damp with some deionized water, which has got nothing dissolved in it at all. I've got one which is a bit soapy, I thought maybe you've been doing the washing up. And I've got one which is a bit salty, maybe you've been clearing up some salt off the floor. And I thought I would try microwaving them and seeing what happens.
So Dave is now taking the microwave plate and putting it in the microwave with his 3 different rags that have been soaked in 3 different solutions. So the deionized water, the salty water, and also table salt water. And the microwave's going now, and also the soap solution rag. So Dave, what's happening? You're zapping these 3 rags with 950 watts of energy?
This microwave is about 650 watts of energy going into the microwave itself. Essentially, a microwave heats things by causing electric currents to flow through them, which is a very rapidly changing electric and magnetic field, which causes things to have currents flowing through them and heat up. Now, the better things conduct, the more energy they should absorb. So inside there, they should be warming up quite rapidly. As they warm up, the water, you can just see on the edge now.
Okay, so what we're seeing now is a huge amount of steam. No, that's not steam, that's smoke that's coming out the side of the microwave.
Actually, I've just smelled it. It is actually steam. So what's happening is the cloth is getting very, very hot. The water is evaporating off that, and it's slowly drying out. Which means whatever's dissolved in there will be getting more and more concentrated.
The microwave being shut, but no, we're zapping it with more energy. We're heating up those rags even further.
So I think when I've tried this before, the salty one actually dries out more quickly than the other ones. This is probably because salt increases the conductivity, so the rag will heat more quickly and so it will dry out more quickly. It's now warming up even more, and now more seems to be
plumes and plumes and plumes of smoke are dripping out of the microwave. This is not one to be done in your kitchens, guys.
So if we examine what you've cooked, what have you got in there now, guys?
Possibly now is the time to turn off the microwave.
Whoa. Okay, and smoke is billowing out of the door now as Dave is very bravely puts his hand in to take out the cloths and to examine them. Dave?
The soapy one is still quite damp, and the deionized one is actually still really quite damp. It's warm, but it's not hot at all.
But that salty one, that's burnt.
The salty one is actually still burning. It's
Don't put your
burning
hands
away
to it,
happily.
Dave.
I can
I'm worried
just
about
pull
you.
it apart carefully, and the inside It's really, really quite singed.
Wow, that's not just singed, there's burning embers going on in there. Can you quickly explain the relevance of this and what's going on?
So the salt is much better at absorbing microwaves than the other two because salt solution is conductive, which is the reason why salty water, seawater, is very, very dangerous if you're anywhere near electricity, because it conducts electricity very well and you can electrocute yourself. And so it was absorbing far more microwaves than the other two. And also salt, when it gets concentrated, increases the boiling point of water. So the salty cloth can get much hotter than the other ones. Also, if you add things to cellulose, it reduces the temperature, which is, starts to char and starts to catch fire. So I think a combination of all of these, and possibly maybe a little bit of sparking between areas which are still wet and conduct electricity and areas which are very dry, cause that one to burst into flames much earlier. So my guess is that Andy's dishcloth was possibly a bit salty. He'd been mopping up some grotty stuff with it, and that meant that it conducted electricity much better, and it caught into flames.
So we now have a car park full of smoke. Dave's just extinguishing the inferno. There you go, Andy. I hope that answers your question.
Yes, that answered my question very well, and I'm sorry you guys had to start such a cloud of smoke to do it, though.
Well, I can't imagine what your kitchen was like. But anyway, they're putting the fire out there. So if you have any other questions or other experiments in mind, Andy, do send them in and we'd be happy to test them for you. Talking of microwaves and things you can eat, here's Hannah with this week's Question of the Week.
This week we find out why our bodies can't get their priorities right.
This is Christian Leixenring and I'm from Bielefeld, Germany. At times I'm really hungry. I'm wondering though why my stupid body doesn't realize that there are plenty of nutrients around my waist, so I would neither have to feel bad nor to run for a cheese sandwich.
So why is it that Christian feels so abhorrently hungry when he's already storing enough energy to digest without involving his digestive tract?
My name is Stephen O'Reilly and I work in the Institute of Metabolic Science on the Addenbrooke's campus. The signals to eat and the signals to be hungry seem to be generated from within the brain. Two of the key signals that allow the brain to access information about the state of nutrition are the hormones leptin and ghrelin. Leptin comes from fat tissue, and probably its most important function is that when we become too thin and the leptin level drops in the blood below a certain threshold, then we become ravenously hungry. However, when we have accumulated too much fat, our brain tends to become effectively deaf to the signals coming from adipose tissue. Ghrelin has a rather opposite effect. It's a hormone produced by the stomach, and it's an anticipator of meals. It rises before we expect to have a meal, and it seems to have a critical role in promoting food intake and promoting our ability to lay down food as fat.
So, the hunger hormone ghrelin spikes before mealtimes, giving us hunger pangs, even if love handles and potbellies are already kindly storing energy for us around our waists. Adding additional weight and an evolutionary twist is Don of Metabolism Dr. Giles Yeo from Cambridge University.
Given the importance that eating has on keeping us alive, our brain has evolved mechanisms to make sure that it also feels good or rewarding to eat, the woo factor. Certain foods, such as energy-dense, sweet and sticky desserts, trigger the ooh factor better than others, giving us the motivation, making sure we store all the extra energy we can. Remember, we have evolved over tens of thousands of years to stay alive through multiple famines, and any increase in motivation to continue to search for food was an evolutionary advantage. Our problem is that after years of natural selection, ensuring that we eat as much as possible to stay alive, we now have to try and adapt to an environment of too much food.
Andrew Wright-Mayer and Aureliano Buenda agree, adding via Facebook that we are programmed to build up energy reserves and to conserve them as much as possible in preparation for times of food scarcity. And our bodies have not necessarily yet learnt to adapt to this new full-fat environment. And this, coupled with a sedentary lifestyle, makes it difficult for us to fit into our summer swimwear. Now rolling over to a similarly themed calorific next question.
My name's Heather McPherson and I'm from Ontario, Canada. I was adding an oil-based moisturizer to my face and I was wondering, does that absorb any calories into my system?
Send your thoughts to Chris at thenakedscientist.com, tweet at Naked Scientists, write on our Facebook page, or join in the debate on our forum, which is at nakedscientists.com/forum.
Hannah Critchlow. Well, that is it for this week. We're actually back in a fortnight where we'll be on the centenary of the sinking of the Titanic, so we're going to be diving down beneath the waves with a deep sea edition of the programme. You can send in any thoughts or questions by email to chris@thenakedscientist.com or tweet @nakedscientist. Thanks to our production team, Hannah Critchlow, Tom Simpkins, Mira Senthilingam and Ben Fausler.
The Naked Scientists podcast comes to you from Cambridge University and is supported by the Wellcome Trust, the EPSRC, the STFC, the Natural Environment Research Council and UK FAST. For more cutting-edge science, join us online at nakedscientists.com.